KiCad. I'm going to call it KiCad because that's what Wayne Stambor calls it, and he's the project lead, so that's good enough for me. It's also says here on the Wikipedia entry that it's also pronounced KiCad. Been around for quite a few years. Started in 1992 by Jean-Pierre Charras at Grenoble, affectionately known as JP within the community. I got interested in it in about 2015, and that was shortly after CERN took it on and started contributing resources. So they put some developers on it full time, and that really snowballed the development effort. Prior to that, I was using Eagle. There are a number of EDA programs around, Easy EDA, Altium Designer, Design Spark from our own RS Components, and others. Eagle I was using because they had a free version. I'm not a full-time designer, so I'm not interested in buying licenses for something like Altium Designer. And Eagle fitted the bill up to a point. It at the time had design limitations. You couldn't design a board larger than, I think it was 100 by 80 millimeters, which is big enough for a lot of Euro-rack stuff. However, it also came with limitations that you had to place the components within the board outline whilst you're laying out the components on the board, and that I found incredibly frustrating. With a fairly dense board, you couldn't place the components well outside the board outline and then just move them in as you were positioning things. So that was frustrating, and KiCad fulfilled my other criteria, which is that any major complex piece of software that I adopt, I want to be open source and cross-platform, and one of those platforms has to be Linux. I don't want to be tied to Windows or Mac OS or anything like that. I'm running Windows here because it's easy for screen capture and that kind of thing, but I also run Linux, and KiCad fitted that bill perfectly. I'm not about to try and video a KiCad tutorial. It's a big program and there's plenty of excellent tutorials on the internet, so if you're interested, go and look there. But what I will say is that, like a lot of EDA programs, you've got a schematic editor where you can place symbols on your page and join them up using wires. KiCad has a huge symbol library, but if you can't find what you're looking for, you can always create your own. And then, like a lot of EDA programs, you can apply different footprints so that once you actually come to draw your PCB, you can use a different footprint according to your application and chosen package size. So, for example, a resistor might have an 1/8 watt or a 1/4 watt, 1/2 watt through hole, or it might be an 0802 surface mount component, depending on the application in hand. And you can apply different footprints to the same symbol within the schematic. And again, if you can't find the footprint you're looking for, you can create your own. And you can also apply a 3D model to the footprint, which means that once you've drawn your PCB, you can then generate a composite 3D model of what the PCB looks like. So that's pretty good. One of the problems I've got is that by default, KiCad doesn't have or won't have footprints for something like this, the PCM1808 or the 5102 modules. So what I need to do is make up my own footprints for these. I'll not go through the whole process, but I've drawn a symbol for the PCM1808, and this approximately mimics the physical appearance of the board, so 6 pins down each side and 3 pins across the top. And then I've also created a footprint for it, and I have created a 3D model of it approximately. I mean, it's not intended to be exactly the same as it. I haven't placed all the components, but it gives you a kind of rough idea of what the component will look like, or what this module will look like when it's been placed on a PCB. In the same way, I've created a symbol for the PCM5102, which again approximates to the same sort of layout as the module itself, and I've created a footprint for it. And this one I did have to measure quite carefully, because if you look at those row of 9 holes there, it doesn't quite line up with this hole I've labelled number 10 down here, so I had to be careful. But I've also created a 3D model of that, which again I've just put the jack socket and a chip on it and some legs, which is pretty crude, but once it gets on my PCB I'll be able to see what it looks like. I won't take you through the entire schematic drawing process. I think that would take a little bit too long, but suffice it to say that the vast majority comes from merely transcribing what I'd breadboarded together, so just connecting things up in exactly the same way. But there are some additional bits, such as the use of a MOSFET here that switches between the VBus and VSys depending on whether you're powering the unit from a 5-volt supply or from a USB supply. This has come from the Raspberry Pi Pico documentation. And this, which is the analog input buffer, I will explain where this has come from. If you cast your minds back to chapter 3 of this video series, I was looking at this, which is a WM8731, and this is from Mutable Instruments Clouds schematic, and this is again it's a 3.3 volt device, and it's a codec, so it has both an analog to digital and digital to analog converter in the same chip, but the chip wasn't very available nowadays. But essentially interfacing this to Eurorack levels is the same problem. And what Emily Gillett has done here is also publish the interface circuitry. So this is the input side. It's taking Eurorack levels and buffering it with dual potentiometers into levels that are suitable for that codec device, and then taking the outputs from it and again buffering and amplifying them up to Eurorack levels. Now Emily has published this under a CC by SA license, and that's a Creative Commons by Share Alike license. And what this means is that I can use this circuitry. I could use it in a commercial product, I could sell it for profit, provided that I attribute where it's come from. So it's come from Mutable Instruments and Emily Gillett, and provided I also make it available under the same license, the CC by SA license, which is not a problem. So these input and output circuits are absolutely perfect for what I'm trying to do. So all I've done is lift the clouds input and over here output circuitry in its entirety. Same component values, same everything. And so it just remains for me to say thank you, Emily. You have just made the Camberwell Parrot hardware design process so much simpler. Another way that schematics can be simplified is through the use of labels. So things like the I2S serial clock, I've labelled it I2S serial clock, and then here where it's used on the 5102, I've just got the same label, I2S serial clock, and again on the PCM1808 I2S serial clock, and this removes a huge amount of clutter because you're not trying to join all these pins up using wires. Another great feature in KiCad is the use of hierarchical sheets. So on this sheet of the schematic, I've got my Raspberry Pi Pico, I've got the Eurorack power, I've got a voltage regulator, I've got the PCM PCM5102, that's the digital to analog converter module. I've got the PCM1808, that's the analog to digital, and I've got the memory chip. But then I've got these other sheets. So this, for example, is the user interface board, which has got the ThonkyCon sockets, the switches, the potentiometers, that kind of thing. And then I've got an analog I/O board, which has the analog input and output buffers, the op-amp buffers, and it's got, this is that little clamping circuit that we talked about a little while ago, about clamping the clock input so that it doesn't bust the input of the Raspberry Pi Pico. And for all of these I'm using global labels. So when I label something as down at this level within one of the lower sheets, I can refer to it on any of the other sheets because they're global. You can use hierarchical labels, and then individual sheets can in effect become their own modules where their detail is hidden, and all you refer to them by is the interconnects, the hierarchical labels that appear on the individual representations of the sheets. But as this isn't hugely complex, I'm just using global labels. Of course, because I've got all of these user interface elements, I've got 6 jack sockets, I've got a couple of switches, potentiometers, rotary encoder, that kind of thing. I'm not going to be able to fit all of this onto a single 12 HP circuit board and still have room for things like the Raspberry Pi Pico, which is quite big, and these other modules. So I'm going to need a second board sandwiched to the back of the user interface board. So I had a quick count up of the connections between things that self-evidently need to be on the user interface board and things that could go on a second board, backboard, and I reckon about 40 connections between one board and the other will be required. So what I can do, and what I've done, is to use the idea of global labels. So I have something that I've called board interconnects, and I've got 4 10-way pin headers and pin sockets, male and female sockets. And so if we take something like the user interface board and we look at the right input jack, its signal I've labeled T1. If I go to the board interconnect, T1 comes here and just goes to the male side of the pin header. On the female side, I've got a label that says RIN1, and RIN1 is this that connects to the input of the op-amp on the input side, and then RIN is what will ultimately go into the PCM1808. So by doing this, I can separate the various parts of the circuit, the user interface elements and the more of the kind of processing elements, power supply, that kind of thing, onto 2 separate boards and connect them all together via these 40 interconnects arranged as 4 10-way pin headers. And by using several pin headers, it means I can spread them out around the board, keep the various connections close to where they need to be, and also it gives a lot more stability if you can spread the connections out.